Today in the Physics Funhouse, we are studying conservation of momentum. You should know already at least one conservation law from chemistry, conservation of mass, but you still may not have a really good understanding of what that word conserved or conservation means. So a quantity is conserved when it remains constant. Constant is the key word there. So when we say mass is conserved, that means that the mass remains constant. When we say we want to conserve water, that means we want to try to keep the amount of water we have constant. And so constant is what it means to be conserved. So what we're going to do to investigate this is we're going to crash some carts together. And so here I've got a picture of one such collision where we take a red cart, which we're going to look at later, and crash into a blue cart. And, obviously they would exert forces on each other. And the key thing we got to remember is that those forces are going to be equal and opposite. Equal in size, opposite in direction. And so I've assigned the force exerted on the red cart a negative sign, make left the negative direction here. And so the force exerted on the blue cart will be the same size, but to the right instead of the left. In a free body diagram form, that would kind of sort of look like this. And remember, that is simply our first understanding of Newton's third law. Red cart pushes blue cart pushes in the opposite direction with the same size force. Now, let's take it one step further. Remember that the impulse on an object is that force exerted multiplied by the time over which it's exerted, and that the impulse is equal to the change in momentum. So it shouldn't be too big a leap to then suggest that if negative F equals positive F, that those two carts being in contact with each other the same amount of time means that they would have equal and opposite impulses exerted on each other. And so since delta t would have to be the same for each of those, when one cart stops pushing, the other stops pushing as well, they won't be in contact with each other, then we can take Newton's third law to also mean that in any interaction, the two objects would experience equal and opposite impulses. So just like we kind of did with Newton's third law in our first statement, the forces being equal and opposite, we're going to take two smart carts and we're going to crash them together with those force sensors facing each other so we can investigate the impulse on each cart and see if they are, like I've claimed up here, equal and opposite. So let's get started with that. Okay, so here I've got my two carts, the red cart and the blue cart, and for right now I'm just going to leave them without any extra mass added. So they both have a mass of 250 grams or 0.25 kilograms, and I've got those connected to the Pasco capstone program. And on the left hand side I'm going to measure the force exerted on the blue cart during the collision, and on the right side the force on the red cart during the collision. So I'm going to pull that up so we can see the collision, and then we can investigate the data after they collide. Here we go. Let's press record over here. Make the screen up big. You can see the data collected in real time. That was loud. Okay, so let's investigate and see what that data looks like. Okay, so I've cleaned up the data just a little bit and zoomed in on the peaks where the two carts were colliding with each other. So here's the force exerted on the blue cart during that collision, and here's the force exerted on the red cart during that collision. And so we can get the impulses by finding the area under the graph. And so I'm just going to click the area button there, and I get 0.17 Newton times seconds, 0.17 Marks. Do the same thing over here, and I get negative 0.18 Mark. So within 1/100th of a Mark, those two impulses were the same size, and again, opposite in direction. The blue cart was pushed one way, the red cart was pushed the other way. So what that tells us is that Newton's third law holds true, and the impulses are equal and opposite just like the forces are. Okay, so doing a little bit of math. If we know that the impulse on the red cart is equal and opposite to the impulse on the blue cart, we can kind of convert that to a general statement that whatever momentum the blue cart gained was caused by an equal loss in momentum of the red cart. And so the momentum gained by the blue must be equal to the momentum lost by the red, since the impulses have to be equal and opposite. So what that tells us is that there's no exchange of momentum with anything outside the system. What is gained by one is lost by the other within the system. So what we can do then is make the claim that the momentum of the two-cart system has to remain constant. And that's what we mean when we say that momentum is conserved. Now it's important to note that is for the system. The momentum of one cart or the other is not conserved, but together their momentum is conserved. So let's see if we can investigate and figure out if that was actually true during our collision. So I've gone ahead and I've adjusted the data to give me position versus time instead of force versus time. And what the position versus time graph will tell me is how fast each cart is moving before and after the collision. So on the left-hand side, I've got the blue cart, and you'll notice it's at 0, and it stays at 0 until about 4 seconds or so. And then it moves in the negative direction. And the negative direction is because the cart was turned around backwards. And so we're just going to make this velocity positive when we actually look at it. And then it kind of continues at that constant velocity after about 4 seconds. If you look at the red one, it starts at 0, and then it starts moving at about 2 seconds. So this is me pushing the red cart, and it moves at a constant speed for a little bit. And then just before 4 seconds, then the position becomes constant, meaning it's at rest. And so here's where its velocity becomes 0. And so you'll notice that this time, where the red cart stops, is the same time that the blue cart starts moving. So before the collision, the blue cart was at rest, and the red cart had a velocity of, let's go ahead and get that. So I can find the slope by doing the linear fit. The red car was moving at 0.339 meters per second. And then after the collision, the red cart is at rest, and the blue cart has a velocity of 0.293 meters per second. And again, it's got a negative sign because the blue cart was turned around, so that it's facing the opposite direction that it should be for it to be moving in the positive direction. So we're just going to take these velocities over here to be positive. Okay, so I've got the velocity before and after my collision. Now let's see if we can determine the momentum of the system and if it changed during the collision. And see if the momentum was conserved in that collision. So before the collision, the red car's mass was 0.25 kilograms. It was moving at 0.339 meters per second. And so if we multiply those together, we get the momentum of the red car, and we get like 0.085 Marx, give or take. The blue cart, since it was not moving, would not have any momentum. Keep it simple. And that means the momentum of the system would be 0 plus 0.085 kilogram meter per second. So the momentum of the system is about 0.085 kilogram meter per second. After the collision, the red cart was at rest, so it doesn't have any momentum. The blue cart was moving at 0.293 meters per second. So multiplying the mass by the velocity to get the momentum of the blue cart, I get 0.07-ish Marx. And add that to 0 to get 0.07-ish Marx, which within, again, error is about the same as the momentum before. Lost just a touch, and we'll kind of look at later on where the error is in this experiment. But within error, the momentum of the system before and after the collision was constant, meaning it was conserved. So you might be thinking to yourself, well, that's kind of obvious. They had the same masses. And so since one stopped after the collision, the other would just have the velocity that the first one had with. So is this rule always true? So let's do another collision where the masses aren't the same and see if we get similar results. Okay, so now we're going to do a trial where one of the carts has a different mass than the other. So the red cart now has a mass of 1 kilogram by adding 3 mass bars to it, and the blue cart's mass is still just 250 grams, 0.25 kilograms. So we're going to back the red card up a little bit, hit record on this, and let's crash it. So you notice in that case, there's a lot larger impulse. Now let's see if they're still the same. All right, so I've cleaned up the data a little bit, and I got the impulse on the blue card. I got 0.18 Newton times second. And then on the red card, I got the impulse to be negative 0.17 Newton times second. So again, within 1/100th of a mark, those impulses are equal and opposite, just like Newton's third law predicts. So now let's get the velocities and see if the velocities show that momentum was conserved during the collision just like it did before. So I'm going to clean this up a little bit. I'm going to switch this back to a position graph. So there's the position of the blue card. I'm going to switch this back to position of the red card. So you can see that the red card starts moving at half a second, and then it moves at a constant velocity till just after 2 seconds. And then you'll notice right here that the line becomes less steep. That's the moment that it hits the red card. So it keeps moving forward after the collision, but it slows down due to colliding with the blue card. So if we get the velocity before and after, so I'm going to draw a box on there, and I'm going to get it pretty tight. And then just before the collision, do a linear fit. So just before the collision, I get a velocity of 0.349 meters per second. And then just after the collision, it slows down to a velocity of 0.187 meters per second. And then doing the same thing over here, get the velocity of the blue card just after the collision, linear fit. I get the velocity of the blue card to be 0.529 meters per second. So again, it's negative because the blue card was turned around facing the wrong direction in order for those force sensors to collide with each other. So we're just going to take that to be positive since we know it moved in the same direction as the red card was moving initially. So let's go back to the drawing board and see if the math adds up and shows that the momentum was conserved during that collision. Okay, so summarizing the data that we just collected, we've got the mass of both the red and the blue card. The red card had a mass of 1 kilogram. The blue card was the same, 0.25 kilograms. And I got the velocity before and after. So let's see if the momentum actually was conserved during the collision. So calculate the momentum in my system before the collision, multiply the mass by the velocity for each object. The blue car was at rest, so it didn't have any momentum, and so multiplying 0.349 by 1 is real easy. I get 0.349 marks for the momentum before the collision. After the collision, do the same thing, only with different velocities. This time the velocity of the blue card is not 0, so I actually need to consider it. Add those momentums together, and you get the momentum of the system after the collision to be 0.319 kilogram times meter per second. So 0.32 compared to about 0.35, that's a loss of about 0.03 marks. And so within experimental error, which again we're going to discuss in a few minutes, the momentum of that system was again conserved. And so we can kind of make the claim that if Newton's third law is true, then the impulses in any interaction must be equal and opposite. Therefore, the momentum is going to be conserved. So when is the momentum not conserved? Is this always true? When does this actually apply? So here's a conclusion that we can make. As long as there's no external net force on a system, keyword in there, system, is 0, that's when the momentum of that system will be conserved. So if there was considerable friction on those carts as they were colliding with each other, we would not get the same momentum before and after. We would use Newton's second law to figure out what happened in that case. And so, pro tip, choose your systems wisely, young Padawans, so that you can take advantage of these conservation laws. So we're going to learn 2 big ones this year. Right now we're learning about conservation of momentum. Later on, conservation of energy. And so if you can analyze a system and figure out a system in which momentum is conserved, that's going to make your life a lot easier. So let's talk a little bit about the error. The way that these carts work is that there is a sensor built into the wheel. And so as the wheel turns, the sensor measures how much the wheel turns by, and then from that it can tell how far the cart has moved. And so, by using the known properties of the wheel and measuring how often the wheel turns in a given amount of time, that's how the cart knows what the position of the cart is. However, that depends on the wheels rotating without slipping. And that's normally true. They roll very well, but during the collision, when the cart's motion is changing very quickly, those wheels could slip just a little bit. And so instead of turning smoothly like they should, they kind of more slide. Like imagine locking the tires up on a car or a bicycle. They slide instead of roll. And so that little bit of slipping, fancy physics word for it, would cause the position to not be recorded accurately, and there's the error involved in using our smart carts to analyze collisions. So as you've seen, it's relatively small, but it is there, so that's why our data isn't perfect. But our data never is perfect, something we have to learn as scientists. So, hopefully, we now have an understanding of the evidence behind the law of conservation momentum and where we might possibly be able to apply it to. So, our next step is to then figure out some simple situations where we can apply the law of conservation momentum to explain why things move the way that they do. Till next time, ta ta.